Good to see that a few courageous people made 8:30 in the morning. I agree with you, it's very early. It's very hard for me to be lecturing at 4:30 in the morning. Anyway, there's a pointer here. I think you'll be hearing more and more from many people about energy landscapes. And what I'm going to do today, my idea is today to show a little bit of the old stuff of energy landscape and simulations, and I will let Cecilia tell you about more advanced models, different level of coarse graining and stuff like that. She believes that since she's much younger than I am, she cannot go over the sort of prehistory of protein folding, so I'll do the work. Okay? But I think you'll be in a good position for her lecture. So this lecture is sort of some preparation for what's to come, and she's going to do much more detailed models than I do today, but at least we're going to bring everything up to a level playing field. And more what I want to do today is the discussion how do we relate equilibrium properties, thermodynamical properties, stuff that you do by just sampling to the real kinetics of protein folding and how we check that from lattice models. And my lecture tomorrow, then I will tell you about, a little bit about a few more interesting stories like some allostery and molecular motors and things like that, and that's going to be separate from what she does. But today is sort of an introduction for both my final lecture and Cecilia's lecture in a sense of where we go about. Anyway, what I told you yesterday, and let's keep that in mind, and that's what we're going to address now, is the following question. That in order to have a good folding protein, you want to make sure that as you have a good reaction coordinate, and we'll be discussing this reaction coordinate, actually Chile is going to address the question of reaction coordinate, but you want your energy to be proportional to that reaction coordinate. If Q is percentage of native contacts, to have an energy proportional to the percentage of native contacts means that you want your energy uniformly distributed all over the native contacts. There's not no one favor each one. So there are two very interesting things that's achieved, and you'll see discussions of that. One is try how proteins have been able to make the native tertiary contacts are attractive and non-native repulsive. Doesn't mean it's perfect, but they do that. So, and just as an aside, you're going to see that if you look lots of experimental data, there is very little evidence, and the little one that we have is very controversial, where you find long-lived non-native contacts. Someone say, oh, I really have a big trap into protein folding, and this trap is energetic because you have the wrong non-native contact formed for a long time. And sometimes this is needed for function, but that's what you have. So that's the first thing. So we said the funnel landscape, on the energy proportion. And the other and the next thing that appears, and I said that in a sort of a naive way for you, but I'm going to repeat it because there's a lot of argument. We said most of these tertiary contacts have about the same stabilization energy. So not only you won't have the energy of the native contacts, you don't want that energy to be too heterogeneous. These are two major big assumptions. And it's going to be interesting going to other different models, see the nature actually achieves that. The beauty of it, we'll be talking about very simplified models, but let me just put a feeling. What you observe sometimes is that when you make a mutation, sometimes you lose on entropy, you lose on energy, but you gain on entropy because at the C alpha level, actually it's very hard to change those interactions. They're of the order, like I told you, typical interactions is of the order kilocalorie per mole of a stabilization energy. Oh, sometimes it's 2, sometimes a little less, but you don't see a tertiary contact give you 5 kilocalories. It will not happen. And you do not see a native contact give you 0.1. It's only kilocalorie 1, 2, that's it. So this, so you'll be discussing it. The other more important thing is if you look at this picture, as I discussed yesterday, I want to bring this up. I put the fact that states that are close to each other in space, they don't have any major kinetic bottleneck, like cross-chain and stuff like that. That's not true. Sometimes proteins have difficulty in dealing with that. Okay? So you're going to address that today. But let's keep that picture in mind, the funnel, and there are the two words. So I'm going to write here, because these words are going to appear on the discussion as we look at protein folding. That's what they call energetic frustration. Okay? And in this funnel landscape, we see what? The proteins, just turn the lights on this. Okay. On this funnel landscape, the proteins minimize frustration. So let's remember what that means. That means that here you don't have competing interactions. A good minimum frustrated situation, you have when you have the native one, all the interactions help each other, right? So you have the native ones help each other, and you are avoiding the non-native ones. That's the first thing. The other word I'm going to write here appears all the time. It's a bad word, mathematical, but since in the literature all the time, is what people call topological frustration. And we'll be addressing that. And I'm going to put quotation marks, but it's a bad word. I also use it, but I'm going to tell how it comes. This word comes as a connection to say that when a protein gets in trouble or gets trapped, this trapping may come from non-native interactions, or may come from geometrical traps, from the fact that sort of you follow something and now geometrically you have to break and go hold back. So it's sort of this word comes as an analog from this one, but this word makes sense. This word makes sense only if you put on that context. It's the idea that you can get in trouble. The first one is you get in trouble by making contacts that are non-native. The second one, you get in trouble by making contacts in the wrong order. I mean, all the native interactions are correct, but sometimes you make one before, there's no way that geometrically you can now make the other one. So you have to, there's an order required. On this picture here, there's no order required. I tell you, it makes no difference to come this way or this way. It makes no difference to make this contact, that contact, that contact, and tell you the perfect funnel. In a system that has no geometrical trouble, or no topological frustration, in the order of forming contact should not be important. We're going to address that. But that's not true. We're discussing when this trouble appears. But I can tell you right now, even before we start, the shapes of allowed shapes for proteins are limited by the fact of saying that you don't run too much in trouble here. And we'll be discussing that. Okay, so with that in mind, let's try to say how this works. Now, this is the figure I showed yesterday. We're going to go back to these 5 values, so I'm going to leave them for the slide later. But I'll tell you the slide. Basically, on this figure here, just to refresh your memory, let's keep this in mind. When you look at experiments, how to relate the funnel to the typical curve you look experimentally comes from the fact that you have like here configuration entropy, here's energy, is normalized energy because solvation is already included. Right, but when you do F minus Ts, you have the 2 minima and the barrier. Okay, this is the scale of these things here. Typical size of barriers for protein folding is around 5 kT. But the size of the traps is 2 or 3 kT. So there's lots of ruggedness in here by the time you look at these things, right? So minor fluctuations, sometimes you see intermediates, sometimes you don't see intermediates. It's not a big deal. This is not a robust property. Now, remembering of that, it's just as a highlight to remember when I looked at curve again, if you're above the folding temperature, the unfolded basin dominates, you're below the folding temperature, the folded one dominates, as expected, right? You have energy versus configuration entropy, you're looking for the transition for TF. And you want TF larger than TG. That's what we got yesterday. How we first investigate that? On the early 90s, there was a great system for that. And before I started to show real proteins, I like this system because that system taught us a lot about these things. And the reason for that is because the system allowed a lot of enumeration, perfect counting, And the definition of a state has no problem because you're in a lattice. So in a lattice, you can literally count. There's no question about how do you define a state. When you go to real proteins, that's a real problem, right? But that's what the idea of the book. This system is what we call the 3 by 3 by 3 cube. This problem many groups did, but I think Eugene Shakovich and I were the first one to play with this cube, that then became an industry of people playing with this thing here. But why this cube is nice? If I give you a chain moving on a cubic lattice, and I'll be careful, but it's a chain moving a cubic lattice, and it's 27 long, right? So I have 27 beads, and they are moving this cubic lattice. The most collapsed conformation is going to be a cube 3 by 3 by 3. That's what I mean by most collapsed conformation. There is the cube root 3 collapse, but in practice you can say that's when you maximize the number of possible contacts between nearest neighbors. Non-bond contact. There are 26 non-bond contacts. So if you forget about the ones that are linked by the polymer, there are 26 non-bonded, non-native contacts, bonded contacts on the cube, and you won't have any other configuration of this 27 on the lattice. That's a good definition of collapse when you form a large number of contacts. Now, the other thing is, it's a very interesting situation that you have into the system, because when people start to work with it, if I ask you how many different ways do you believe you can fold a 3 by 3 by 3 by different shapes, how many different ways can I do that? It's a very interesting thing. Those times I remember that was sort of a typical question to give to, that time was 1990, we didn't have fast workstation, that time we used to work with SGI workstations, was always a problem we gave to students, how do you solve that? And it was very good to know they knew anything about computer science, right? So basically, most people could come up with the right answer, but some people would spend like 3 days of computer time, some people would spend 2 minutes. Right, so basically it's like they got people that knew how to do elimination, right? You do seeds, you don't do all the things, you do seeds, and when you run on dead ends, all the things that come from that one you throw away, they could do very fast. Right? You can really use these elimination things very fast, but if you really try to simulate by any other way, it can become a total nightmare. You can do, but you can spend a lot of money. But just out of curiosity, there is 103,346 different, what I mean, symmetry-independent states that are here. That means we're throwing out all rotations and reflections and things that are symmetry equal. Right? And by that we means I characterize a cube by its list of contacts. Right? That means I say this cube I have residue 1, connect residue, whatever, 11. So if I make a list of the 26 contacts, that means equivalent to throw all the symmetry-related configurations. Right? So if you make a list of the structure is the same context, you have these ones, okay? By the way, this sort of symmetry is a very important one, particularly when you run reduced models. I think Chichi is going to tell you a little bit about, but if you run reduced models like C-alpha models, models like that are very reduced, and you have to be very careful with chirality. Sometimes you form chiral traps, but these problems don't guarantee chirality, and you run into big troubles on things like that. But it's one of the problems in simulation. But this is what you have. Okay. So Nick Soch only group at that time, and we decided to play the game. I'm going to give you a little bit about that story. We said now we're going to try to design sequences into this cube. So here are some numbers for you. So what we create is the following problem. We said there are two kinds of interactions. An interaction, let's say, when residues have the same color, is a strong attractive interaction. And when residues have weak color, is a weak attractive interaction. That means we're characterizing the problem by two parameters. There's an average number that I will tell you that's like -2. That's forcing collapse of everything. That's what we call uniform collapse. Non-specific collapse. That's what I call this parameter E average. And there is this delta that's also 2. Let's say, from this -2, I have a -1 if it's the same color, another one if it's different color. So basically every model you do here, in folding these days, you say how much specific and non-specific collapse you have. The specific one is when you have the chain difference. I could have a system where I say, where I put this average Could put this one here, even repulsive, or I could put like this one 0 and this one -2, for example, or whatever. Tell you that just one is attracted, the other one doesn't care. But you can play. So this is the sort of situation that we did. This is a good number. This is actually an interesting number. Maybe it's a little bit too large for proteins to put the same number on average and delta here. Proteins maybe don't have so much collapse. But you're going to see also when we do a loop of Go models, people do it. They're very good to reproduce experiments, but the unfolded base is a little bit too open, too diffuse compared to real proteins. So they have even the unfolded base a little bit more collapse, which means there is a certain number of non-specific collapse. But that's just curiosity that you're going to have a chance of seeing as you start to do models later on. But this was just a simple model that tells you now I'm going to create chains into this system. The chains is I'm going to create chains that are beads of blue beads and red beads. And since I have 27, I get 14 of one color and 13 of another color. And now I just change the order of them. And the question is, if I choose one of these 103,000 possible cubes, can I design a sequence that folds to them? Like I said, the number of contacts at 26 is actually 28. I should remember here. Z would just say is any contact, and Q is the one who really uses correct contact. Contact is equal to the native one. So this was a nice, cute system. This system here, I don't know if I have any dynamical data here, but I can show you. Oh no, I will tell you. The systems are very fun because these are not things we create. These things come from polymer physics. They're very typical models of lattice in polymer physics. And they have several possible move sets for this system. So how do you move? You do what you call Monte Carlo kinetics. I had a particular chain like that. And I get a bead at random. So which are the moves that are allowed? How do you do dynamics here? You go to the lattice, and if you have an end group, a group like that, you assume that you can move any place here, here, or out of the board. They can move in any direction, right? Make any of these moves. If you have what you call a corner move, like that, you assume that this corner move can move here or there. They can move as what you call, so you have end move, you have corner move, and sometimes when you have situations like that, you can have what you call crankshaft. Okay, they can move like this entire piece, can move down this way or that way, right? You move like a crank. And that's actually very interesting. You can define a full kinetics. They're very sense to reality. The only thing when you do kinetics on lattice, you have to remember, you decide to make a move, you get someone at random here, it's a crankshaft, you try to move up or down, okay, these are the two possibilities. If the space is full, you have to count a step. So the first thing is, if it's occupied, it is a step. Some people say, oh, you only count occupied. No, then you get total nuts dynamics. There's no sense of connect to reality on the system, because the system actually, if it's full, it tries, it collides, it doesn't move, okay? So what these people do call Monte Carlo kinetics, so we have two things. First, you see if it's occupied. If it's not occupied, you compute the energy of that state compared to the previous state, and you accept based on a Monte Carlo move. What's a Monte Carlo move? If you go down in energy, you accept. If you go up in energy, you accept the increase of probability E to minus delta E, the difference of energy over time, over temperature, right? So this is the typical, is that a real dynamics? No. But these people working with polymers know you can learn a lot about real dynamics out of these things here. For us, it's even more interesting because there are different probabilities you can put in addition to these things. And we learn that precise choice of move sets is not that important, as long as you don't think about absolute times as important. If you just compare fast and slow sequence and you look at the ratios of them, these ratios are about the same, independent of the precise move sets you do. There are a few things you notice. For example, if you eliminate the crankshaft, you see crankshafts are not allowed, you notice very fast lose ergodicities in the system. So there are a few things that you learn from polymer physics, don't have time to go here. But it's nice. So the nice thing about these systems here, they're very fast. You can start with extend random chain, and let it run, and let it run, and see if it folds to a particular collapse form. Right? So this is a typical state in the middle of the trajectory, and you just let these things move. Anyway, when you do all these things here, the first thing you do is you do lots and lots of sampling, like everybody did simulations. And basically, there's lots and lots of secrets of running sampling. And if you never have done these simulations, I think the papers that Nick Sochi wrote with me, there's a series of papers that came in the Journal of Chemical Physics, and I'm writing the names, I don't think it's on your list, but they are like Sochi and Onshik, they're the two authors on these papers. There are several papers that came in the Journal of Chemical Physics. They're sort of very nice papers if you haven't done, because they tell you a little bit about sampling. They tell you how are you sure that you're satisfied with sampling. How do you look at error in simulations? If you go to simulation field these days, there's a problem. In almost no simulation paper, people tell you what the error bar is, or what they believe it is. Do I have enough sampling? Do I have enough things? And basically, that's a very, very important question. And you may hear from Cecilia, when you start to do multiple temperature simulations, and you start to do RAM, and you start to match different trajectories, there's lots of very interesting questions that tell you, how are you sure that you have? And it tells you how you run multiple simulations, how you look the mean of between the simulations, how you get half of your data and compare to your total data. There are many different ways you can do to give you what we call simulation error. There are two kinds of error when you run a simulation like that. One of them, there's nothing you can do about. But the other one, you should do about. The only thing there's nothing you can do about. Let's assume there's a particular region of the configuration space and you never go there. But the barrier is so high and everything's so calm, you never go there. Then, if every simulation you run, you never go there, there's nothing you can do about it. It's going to appear like it doesn't exist. For all practical purpose, and when you do numerical error and all that, there's always something that's twisting your stomach to make sure that you have visited every area you want to visit. But normally, if you have a good experience, you know that you have seen everything you want. The other one is to make sure that you have enough sampling. Okay? And having enough sampling is an interesting question. So if I shoot the next trajectory, I run lots and lots of simulations here. And when I run the simulations here, I just count which state I am. And when you run a simulation, you're going to keep track of two things here. I'm going to say what I'm going to keep track as I start to run the simulation. You're going to count every state. So you're going to figure out how many states you have. We're going to write N. It's how many times you have visited each state. But you're going to make a table. But N as a function of what? In this problem, in every problem, you have to keep track of the energy. You have no choice. The energy is there. You cannot do anything thermodynamics, right, if you don't keep track of the energy in a simulation. The other thing here can be a constant temperature, Grand Canyon, whatever simulation. The other thing is, you're going to keep track of every order parameter you want. On this particular case, I can keep track of Q. If I want to keep track of Z, or just one of them. But if you're interested in any order parameter, later on, you also have to keep track of them. Now, why I put these three dots here? You see, on this sort of lattice model, it's easy. Off lattice, you have to bin things, right? Because they're continuous. And bin's a little bit more complicated. So binning, that's where your resolution is. Lattice is great because your resolution is given. It's a discrete problem. But remember one thing, just as you do simulations. The more things you want to keep track here, the more sampling you're going to need. Right? Because you're making a smaller thing. If I want to keep track just like E, let's assume that now I want to say if every contact 1, 2, 3, and 28, if they're formed, what we call individual Qs. I don't ask at every state How many contacts are formed? I asked if every individual contact is formed at that time. So now I'm going to get 28 variables here. Right? And that tells me I better keep that sample. That could cost me. Sometimes that's what you want. It's not a problem. But remember, every time you do sampling, the more things you want to keep track of, the more you have to sample. Now, if you do that, and you get these states, actually, basically, from this occupation, if you're running at constant temperature, you may even have these things, let's put temperature here, or whatever other sampling you have. You can correct for the temperature afterwards, and get the absolute state, the full density of states. Okay, so first here you measure some probability. You can sort of use your exponential weight back. And in the end of a big run, that's the quantity you get. Right? Actually, simulation, measure what we call like P of E, Q, in a sense that something is temperature dependent. But that's very easy to be converted back by temperature back. If you have what you call your density of states, now you go back to your thermodynamics course or statistical physics course, and you can get any thermodynamic quantity that you want. If you want to know what's the entropy as a function of whatever, right, you're going to have some integral or Legendre transform, and that's straight, cranky, no big deal, that's easy. So the goal of every simulation is to get this density of states or this probability. They are equally related. If you have either of them, you can do that. There are some simulations that you run these things on multiple temperatures and match things but this is just a question to have better sampling. This is just numerical tricks. In principle, if you run a single temperature and you have a good quantity here, you're done. You should be able to have this quantity at every temperature and all that. In practice, that's not true. That's why there are all these sampling tricks out there. Run canonical scheme. You try to force your system to go to regions that you don't visit too often, and then you correct for that, right? Always the same way you can correct for temperature to get this one, you can correct for any other constraint you have in your system. And if you look at these things, it's great. You just go around, you're going to see many papers. So that's the idea. But remember, the main goal is to get these things. No matter which simulation you have, that's your main goal. After you have that, then you can start to draw figures like that. But people say, where do you got this figure? Oh, that's a very simple one, right? Basically, this is my free energy as a function of Q. That means what? If I have this E and this, basically, N of E and Q, I can very easily write a partition function for that, of E and Q. And from that partition function, the logarithm is going to give me a free energy. You could get the entropy, you could get everything now, right? So, but that's what we want to put here. Now, this is not a real free energy. Remember what means a free energy as a function of a variable. If you have a real thermodynamic system, if you have a real, and that's a very important concept that I want to tell you, and people now are very cavalier about it. And I have seen many young people that go in there, and the things became so mechanical, they have no idea about what they're doing. So I don't mind spending my time telling you at least one time in life what these things mean. If you took a course of thermodynamics, you say, what means a free energy is a function of Q? You say a free energy is a free energy. If I have a system, if I do thermodynamics, it has an entropy, it has a free energy, it has an enthalpy. What that means. That's what I learned in thermodynamics, but people keep showing me these things here. So what I'm doing here? What I'm doing here is the following thing. Normally, you have just your density of states in terms of energy, you get these numbers. Now let's assume that externally, you are able to control a system. You're able to say, I'm looking at this cube, but I have an outside constraint that I put on my system. In addition to everything else, there's another outside constraint that tells my system that Q is fixed into a number. So I'm telling you, not only I'm doing my system, but I'm doing my system, but only the states that have Q equals 16 counts. All the the other states don't count. Okay? All the other states don't count. Right? So that's what the problem is telling you. So now I'm computing a free energy, assuming that something else on the outside is constraining one of these things. It can be any constraint that is on your brain right now. I don't care what it is. It can be as stupid as you want. I want that contact 1 and contact number 18 is made, and I want to make sure that contact 22 is not made. You can make any constraint you want. Right? It's like saying only the states. So if I have my full dance of states, only states with a particular constraint count. So it means it's a way that you can think that your physical system now is limited to that constraint. So what that tells me here is what the free energy of that system, of one particular cube. I'll tell you, that's a very good design cube. I'll tell you about it in a little bit. What the sequence is. Here I'm just showing a free energy for a well-designed cube that can fold. And I go back here. What I'll tell you is this free energy has this value here, comes down to this value here. This is a particular temperature here that they call default. When you're 50% of the time here, 50% of the time here. It's a finite system. That really tells you that's the value of all the free energy. So if I ask you what's the real free energy of the system, it will be around here because you minimize all these free energies, and that's now if I minimize F energy in terms of Q, say what's the most likely Q, that tells you what you are here. So, but that's what you get. Now, why do you care about these things? If you're just doing thermodynamics, say, oh, that can be a useful thing. I compute this thing here, and now I figure out where is my minimum here, what's the most likely Q based on how does that free energy has. And you know that finite systems, only infinite systems are going to go to the absolute minimum of the free energy. Finite systems can actually fluctuate around it, so you can think about fluctuations here. That's why it's great to do these things here. Right? So, that's what you're learning. Now, some people tell you, I told you how to compute a free energy as a function of reaction coordinate. But then you open all these papers and people say, oh, this is not a free energy, this is a potential mean force. I say, what the heck that means? What means this PMF? And some people say, oh, I compute a PMF. And then you can find students say, you compute a PMF. What PMF mean? I have no clue what PMF stands for, right? They have been computing PMF for their life. So it's good to remember what means a potential of mean force. That means that now you're going to do an extra step. Here, I'm just doing a statistical physics approach. Basically, you're able to do, you write your free energy as a function of any parameter you want it. You hope this parameter has some physical meaning. You can call another parameter here. But the question now is, the next step is this parameter a good dynamical parameter? And that's what we're going to go about. What I would like to tell you is that this parameter, if this parameter is a good dynamical parameter, then I can tell you not only this free energy comes from this calculation, a good one. Actually, dynamics of my system, I start around this minimum, then I overcome this barrier, and then I come towards my folded state. Okay? So that has been the real challenge. How do I guarantee you that actually that's a good representation of the dynamics of the system in such a way that now I'm showing you a free energy profile. I can tell you that the barrier that I got out of a simple sampling approach, I don't have to run full kinetics here, just from sampling. This barrier is the bottleneck for the kinetic problem. That's a big if. There's no guarantee a priori that that's true. Okay? There's no guarantee a priori that's true. And that has been the big challenge about getting good reaction coordinates. If that's true, and we believe that's true for energy landscape, then you're in very good shape. Because you're doing problems when you're just doing sampling, and you are out of sampling approach, you're making kinetic conclusions. What's a fast folder? What's a slow folder? When you never measure any time. So that's where the potential mean force comes. But there's no guarantee that's true, a priori. There's not like a theorem that you check here and do that. That's why we played with this system. So out of curiosity here, for you guys, this is sort of a nice plot. This is a good folding sequence, and I'm going to go over this thing. Here now, I put free energy. The terms here, you see minus 84, minus 8, they make sense. Why? Remember I told you I have a maximum 28 contacts. 28 times minus 3 is minus 84, so that's just all these funny units we have here. Typical folding temperature for the system is 1.6 on these funny units. Whatever this unit is, if I tell the unit is in units of energy, this is a temperature on the same units of energy. kBT is 1.6 for the folding temperature on this system. I'm going to show you a little bit. But you see, this is sort of a kinetic run, measured on these steps, Monte Carlo steps. And it's very nice, because now it's time, okay, this is time backwards, if you want to run. So they took about 1 million steps to fold here. So now this is time, what you're seeing is, you're oscillating around this minimum here. Then you try to come down, you don't do it, you try to come down, and then finally you diffuse down this way. Okay, this is sort of don't worry about this peak here, this is a lattice artifact. You never visit the states down here, so, because they don't exist. It's very, you normally jump between 26 to 28, and so basic, so don't worry about this peak here. This is really a lattice. This lattice is finite. But it's nice to tell you that really this problem is like a diffusion over this barrier coming down. At least pictorial. That's a typical trajectory. So that point makes you feel good that actually this is really the barrier you're trying to overcome. I show you a problem that came out of sampling, and then I show you a kinetic trajectory and say, okay, this appears to behave as a good reaction for you. Now you can quantify these things better. And you're going to quantify these things better. Right? But that's the important thing. So at this point, I think you understand what a free energy is. That all you have to get is density of states as a function of energy and all the other parameters you want, and they're tools of tricks and reviews and stuff like that. And they can be very useful for you. But it's very important to understand what you need. A lot of these reviews is how to do this to work better. Because sampling is a tough thing. How do I know I sample enough, what my error is, right? How do I have enough? And from this one I can get any quantity you want. Now if you want your free energy or your potential mean force as a function of some particular order parameter that you want to make a reaction coordinate later on, whatever you want to, you have to keep track here. You have no choice. No, it's not like you cannot run an entire simulation. No, but that's not how you want. Oh, forget it, kid. Start from zero again. If you don't save the data in there, so you're always here, right? You're always making a choice. How much data I'm saving? Increase, oh, then let's save everything. Oh, then you're not going to have enough disk space. So there are trade-offs. And the more stuff you want to save, the more simulation you need, because it's like making beings that are smaller in the space, or force more variables, you have to keep track of more things. So it's a trade-off, like everything in life, when you're having a feeling about it. So let me go over and tell how, I told you that's a good sequence. So this sequence I showed you, that simulation, we're going to go back to it. I just want to show it before, and now we come back to it. These are a few sequences that we simulate. We simulate lots of sequences here. Forget about this figure for one time. We'll come to it in a little bit. These are many, many sequences here. And I just gave the names of those sequences. Means you have two bits, green and red. Here we're just calling A and B's. Okay, and I show you several sequences here for your curiosity that I want you to have a look. So what I'm telling you here is just look this first sequence here. Let's remember for time basically. So if you're looking this sequence here, forget about the two bottom ones, we come back to them in a little bit. But 2 and 4, out of curiosity here, 2 and 4 are sort of the best sequences you can design using just a 2-letter code, just 2 kinds of bits. And if you look at this sequence here, and I use my numbers into this problem, you're going to see that the TF is about 1.285. You're going to see what I mean that. And TG is about 1 on these units. That's when you get glassy. And I'm going to tell you how these things are observed. Just give me a second. And I notice, and this is give a TF over TG 1.3. If I want to do better into the system, I have to use at least 3 different kinds of beads. That means I make my life easier, right? If I tell you that now red likes red, blue like blue, and now I give the possibility of green likes green, I make my life easier to design, right? The more beads I have, the easier it is for me to design. Now, why can you do better when you go to a 3-letter code? I'll tell you, there are 2 ways you get better. One of them is you want to make sure that your native state has only attractive interactions, right? They all help each other. So if you look here, these are native interactions, these are native interactions, these are all native interactions, okay? It's all nice. So is this one, the 3-letter code. So they're both equally well defined, designed. They only have native interactions here. However, as you start to move and unfold, you start to see that basically this blue bit may bind to this blue bit on some unfolded configuration and make what? An energetic trap. That's not going to happen here because these ones have different color. So this is an optimization problem, TF over TG. Optimization problem means that you always have 2 things. You want to make your target state more attractive, but you want also to make the competing states less attractive. So it's a ratio of things. Right? So, and that's what's doing here. Most of the way to improve from 1.3 here to 1.6 here doesn't come by making a better design of the native state, it comes by pushing the traps further away, making the system. On that figure I showed you yesterday, remember the figure I showed you yesterday, just for fun, I'm going to draw here. If I put my sort of density of states as a function of energy, remember I said I have my continuous of states here, and then you have the few states that comes towards the native state here. Right? So this is the story. So there are 2 quantities that you want to optimize here, and that's pretty much what you're doing here. One is what you call the energy gap. The energy gap is you want to make sure the typical energy from the average trap state to you gets larger. That comes by doing a better design of the native state. The other one is this delta E here. And I want to make it smaller. I want to make my traps less traps. And how do you make this thing with less traps? You make these things by having large number of bits. Because remember, your TG depends on this delta E. Right? So these are the 2 things you want to do. You want to push your states up here, but also want to make distribution errors, like to make less and less deep traps. Remember, the typical trap was what? Minus delta E squared over T. So it's smaller delta E, you make your traps more shallow, typical traps. So that's the game. That's all these things can relate to the physics. And that's what you're trying to achieve here. So, but this, what we have here, and the reason I'm presenting you all these figures, is I'm going to show you some results for these figures and how we have achieved these things. So let's see a couple more slides towards this goal. We have a few sequences. Let me see what I have here. I think I forgot what next one is. Okay, here's my good sequence. I think this one is diffusion in Q, and let's go back just to make sure that we are correct here. Here what you're looking at is sequence 12, the 1.6 sequence. Okay, so I'm going to show you some results for the simulation for the best sequence we have here. Okay? So this is the 3-letter code sequence just out of curiosity. I'm just going to show, I could show for the 3 of them, but one of them is enough to make my case. So if I get that sequence, I think comes with these plots. They're sort of a very interesting plot, particularly if you are a physicist. What I'm looking here, basically, what you're looking here is data out of the simulation, out of two particular ones. So the points are sort of simulation results at different temperatures. So let's just look at the points right now and forget about that formula for the time being. Forget about the formula for the time being. So these points tells you the following thing. If you notice is the temperature is too high. Now it's beta. Beta is inverse of temperature. So temperature too high is here. Beta is 1 over T, right? Just for curiosity. So if I'm running that good sequence at high temperature, my folding time, guess what? Long. Why? Because the system never collapses. It's very happy to be expanded. So you start to lower the temperature. Lower and lower and lower. And see what happens? Your folding time starts to get faster, 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 faster. Until you, what happens? The temperature gets so low that now you start to get trapped. You start VTG and you see your folding time goes up. So you have this window of opportunity, if you look, that happens between, see here we came all the way to 1, after that you're very, very slow. So here is temperature. Here is many simulations that you have been running. They run many simulations and figure out what's the fraction out of these many simulations, what's the fraction of unfolded states. These lines here that are drawing here, these are sort of best exponential fits to these systems. So what you see is on temperatures that are fairly low, I know it's hard to see here, at least for me it's even harder, this plot doesn't help you. You see things all the way up to 1.12. They're really, see these things, they're really falling on exponential. 1.509, 1.26. The fit to exponential is perfect. So this is not a fit, by the way, I'm sorry. This is to say, I get my mean first passage time on these problems. And I say, are they exponential? And you see that the mean first passage time just falls on these processes are totally exponential. So since at high temperature, they really fold as an exponential, overcoming a barrier and doing it. As you start to get 1.12, you already have a minor deviation for the exponential. But you can see here, you start to have big deviations for exponential. That tells your system is starting to get trapped. So you can almost identify what you call the glass transition here, not only by having a slowdown here, but also by observing that basically you're getting to a situation where your system is becoming really glassy. So that's very nice because you see this sort of how this basically, what means becoming exponential? It means that basically you're not just going back like I showed you before, you're not just you're not just overcoming this barrier here, and you can say these things, but you can do that. So what we did here, now, on that plot, one more time, is we try to say, is that a good model? There seems to be a reaction coordinate. How do I check there's a good reaction coordinate? So what Nick Soch did was another thing. He came here and looked at relaxation around the states. What he did is a QQ relaxation. You look at your Q coordinate just around the unfolded basin. And on times much, much shorter than the folding time, you can find what this relaxation time is. And based on this relaxation time on the unfolded basin, we wrote a diffusion coefficient for our process. And said, now, can I describe the system as being a diffusive process over this barrier with the diffusion coefficient that I get from that basin? This is actually very important because remember, when you do more detailed simulations, you cannot do full-time simulations. So if you can relate these two things, you can do that. So our idea is, can we talk about this being diffusion on this free energy profile? And what these results show here, these two lines, they're actually very interesting. They're two lines, and they're just different approximations of how you do this integral. One is just use the simple formula, the other one is really do the integral numerically, and tells you that basically they actually agree quite well, with the difference that basically the results of the analytical things are even a little bit faster. Would you expect these things to be faster? Would you expect these things to be slower? They are always going to be faster. And the reason for that, I'll tell you right up front, this is actually pretty good. These things are varying by a factor of 2. Then on this precision, this is a log plot, so if you see this is actually just a factor of 2 here. So this is actually a very nice result because things really slow down substantially and then you fall on a plateau, and that's why you plot on the log plot. If I don't plot log thing, if I plot on a linear scale, this thing will look perfect. But it wouldn't help you to get numbers out of it, right? So I want to fool you to say how great, but actually just tell you by factor of 2 you can do that. But tells you you can go pretty close on computing these rates out of the expression. But actually, Cicilline is the expert on that, so let her tell a little about. The reason for that here is, when I did this free energy profile here, and I come over this barrier here, when I do my integral case, I'm assuming that every state on Q17 is able to go down to fully fold. And there are a few states that's not true. These reaction coordinates are not perfect. They're good, they're not perfect. So there's a small percentage of states out there that actually you get geometrically trapped and you have to go back and try again. And that difference tells you that maybe not 100%, but about 70% of the states here are good, but tells you that's a damn good reaction coordinate. But it's not perfect. And when I assume that every state should help me, I get a little bit faster. So it's a way that actually, in a sense, the real barrier is a little bit higher because not every state, right? In a sense, when you compute the entropy at Q equals 20, you should correctly say that not every state here is actually productive. But you never can do that in practice, but tells you that's a good reaction coordinate. So the reaction coordinate, they will give you more states that are productive, the better it is. But that's what's given to you. But that's the idea. So that's the idea behind all this sampling. So now, until a last slide on the lattice, and then I'm going to try to summarize all this. This slide is one of my favorite slides. If you have me work on protein folding, there's a quantity that people call phi values. We have phi values. So let me tell you what phi values are. Like I told you on my funnel picture, if I believe my energy is perfect, and the order of the contacts makes no difference. If I come here, and I look at the top of my barrier, that's about halfway through. Tells me that in the top of the barrier, I have 14 native contacts formed. If you believe the world was ideal, then it'll tell you if I look all the states, and I sample over all these states, and I have 14 possible contacts. I have 20 possible contacts. They all should exist with equal probability there. In some configuration, you have this 14. In the other configuration, you have the other 14. In the other, you have all these contacts should be the same. So it means on the phi values, people experiment tells you what's the probability of a particular contact or a particular residue, as you're going to hear. It's not, they don't see contact, they see residue, but let's give these contacts here. What's the probability that C be formed in transition state? If I have this perfect funnel I told you, should be all with 50% probability there. That's not true. What you see actually is that some contacts are more likely to be formed in transition state than others. And the origin of this heterogeneity comes from what? From geometrical limitations or from energetic limitations. The case, okay? And that's what people measure experimentally. And I'm going to make my case that this comes mostly from geometry before we go forward. But let me be a little bit more precise about it. So what people measure into phi values, and if you go around, everybody tells you that a phi values comes from experiments where you go and you make a mutation. And when you make a mutation, you ask, how much do I change my barrier compared to how much I change my total stability of the protein? Okay, if the world is ideal, if a particular contact is already formed, if you make a mutation that destroys the contact, then what happens? You increase the barrier by the same amount. If the contact is not formed in transition state, what happens? Nothing happens. Right? So if you do a mutation, and you could measure these things here, okay? And you could measure these things here, will tell you how much a particular thing is structured in this thing. That's something that's been devised by several groups, most of Alan First, but started by people like Bob Matthews, many people, a way that experimentally to probe which parts of the protein are structured at the transition state. Anyway, that's the idea between phi values. So, and if we believed this was true, we should expect this number to be half for everything. Tells you it's about 50% for every quantity. It's important, it's a ratio that makes no difference on how big the mutation is. That's why the ratio does give you this probability. It's not all ideal like that, but let's leave on the ideal world for a little bit. That's what the experimentalists claim they are measuring. That's not what they are measuring, but that's what they claim that's what they are measuring. I will tell you why that's not what they are measuring, but let's stay for a little bit. Now, what I did here, the experimentalists actually don't measure that, because there's no way experimentalists that have a free energy as a function of Q. That's a theoretician luxury to have that thing. They actually have to measure rates. So actually what they do is, instead of measuring how much your barrier change, they measure this quantity here. How much stability change that they can measure. But they measure this minus RT, the ratio of the rate after the mutation by the rate before the mutation. If you believe, now is the important thing, that your system is really a diffusion on a free energy profile, that means that your prefactor, your diffusion coefficient, is very little affected by the mutation. That's true on a good smooth landscape with a good funnel. But all you're changing is the barrier. Then these two things become the same. But if you create traps where your prefactor gets affected, these two things are not related. So although experimentalists are always assuming, even without accepting sometimes that they have a great landscape, because they are saying that that's what they're measuring, and actually that's what they're measuring. This is only true if you have this situation. So you expect when you do a mutation on a protein, you're not creating local traps. The major change comes on change the overall main barrier for folding and all this sort of a typical roughness that comes on the diffusion coefficient, that thing's not changed. That's a great thing, because it really put us in a right perspective to do. So the lattice was great, because the lattice allow us to check these things. So what we did, we decided to measure 5 values for this context, for my lattice model. But we got 3 models. Here, this is the model I told you about, the one I just have been showing you, the 3-letter code model. This is my 2-letter code model. And I will show you what this plot means. And this one is a model what we call a structure-based model or a GO model. And people see, this is a model I don't even have the 3-letter code, I have the ideal model that you know. It's a model where I say native contexts are attracted and they only interact with themselves, and everything else is repulsive. That's what we call a structure-based model. These are the ideal models. I'll tell them about it. Chile will tell them about them, how you work about these things. But these are models where you assume that only native contexts are attracted. So there's no way of forming bad states on the unfolded basin, right? Because you're never going to have the wrong contact form. There's no chance you go back to have like a blue, make a contact with the wrong blue, because like I'm only a now native context. So what's great about this plot? Here I have what I call phi kinetics and phi thermodynamics. Well, that means the following thing. On this model on the lattice, I can actually measure my folding time I can measure this by seeing how much my barriers change. But I also can compute these rates. I can actually run lots of simulations and do the kinetic rates. So if you look in the middle of these things, what this thing tells you, here's phi kinetic, phi thermodynamics. You see, you have some regions of high phi and some regions of low phis. But they agree with each other. What tells you is, if you're glad with a precision of about 10%, 20%, they agree with each other. That's a great situation. Tells you this approximation is not that bad. You can really figure out where they come from. So you're not doing bad. That's a good thing. If you do the model, basically, have the real GO model, it's even better with less fluctuation. But they agree. The region of high phi is the same region of high phi, the region of low phi. Well, but the GO model has no energetic frustration, because by hand I took the energetic frustration out. So you know that this difference, which formed earlier before, comes from geometrical aspect of people call topology. And you know the three ones good enough. Some things can be formed before because of the topology and geometry of the problem. And that creates a situation where people tell you that, so that's why GO models are good for proteins. Although proteins are more like model like this one. You can see, you can predict which contacts are formed first or late from this ideal model. Because you know that most of this distribution of high phi's and low phi's come from the fact it's not true that every contact can be formed in the first order. There's a question how long is the loop, and some things have to come early. So you're in trouble. My two-letter code, look at this thing here. They're all over the place. That means this quantity doesn't agree with that quantity. This system is too rough. There are too many traps. The FAPERJ here, remember, this was 1.3. That's too much trapping for you to do this thing. Proteins are better than that. Proteins at least on this 1.6. That's the protein world. But this is just telling you that basically, if proteins were like that, typical 5-value experiments would mean nothing. Right? But on the lattice, they give you a feeling for these things. Okay? And you can measure all these quantities. Right? This is sort of nice way, because we'll be talking about 5 values and things like that as we, today, tomorrow. Today we have another 20 minutes, but today, tomorrow to bring back, but that's what I want people to remember. So this, on a simple lattice model, I gave you a couple essences that I hope you guys keep on it on every simulation that you do. Basically, what's the scheme of simulation? Sometimes you're not going to be able to do simulations, sometimes you're just going to be able to do sampling. And when you do sampling, you get these free energy profiles. There's an underlying assumption telling you that as long as the landscape is sufficiently smooth, that means a sufficiently large FAPERJ, you can relate thermodynamic quantities to kinetics. You can say what's a slower folder, a fast folder, by just comparing this measure that you got from a free energy profile. You shouldn't be able to do that if you had a very rough landscape. Okay, so that's one of the nice things that come here. If you look these days, there are very interesting things in terms, I just want to go back one slide, not this forward, back one slide here. There are lots of works on these days on trying to compute this diffusion coefficient. These things on this lattice is sort of a zero-order model. This was sort of the kindergarten of this approach for this problem, but actually people were kind of serious. This diffusion coefficient may always depend on Q, may not be something, because may depend on the growth. There are lots of stuff you can do, but the overlying essence is in there. Right? So this is the idea of running the simulations. This is the lattice. That's why lattices were useful. Lattices allow us to investigate these concepts of what is free energy, what means a potential of mean force. So if you think about what means a potential of mean force, there's nothing that